Okay, well, welcome everybody in Chicago, in Geneva, and I'm really happy to have Dean Rickles here to talk to us about duality. I'm going to turn the sound off, Chris, so email me if you have any issues.
Okay, well, thanks for making me give a talk at 9 a.m, Chris and Geneva folk. It's terrible. So this is a talk about dualities and the interpretation of dualities. So you heard quite a bit, I think, in this seminar series. I think Richard was here last, Richard David, talking about empirical equivalence and dualities. My talk is going to be covering fairly similar ground. What I'm basically going to be doing is arguing here, however, that dual theories are basically just examples of gauge redundancies. The theories themselves are basically like gauge degrees of freedom. Okay, so I don't know whether everybody knows what a duality is here, though, so far. Do we have like non-insiders and stuff? Okay, so this is like totally the wrong coast, I know, to talk about like yin and yang, and it should be in California or something. But there are quite a lot of similarities between the yin and yang concept in Chinese cosmology and dualities, right? So we have these two complementary characteristics in Chinese cosmology, right? You have your light, your dark, your passive, your active, your feminine, and your masculine, and the idea is that these are together generate the properties of the universe in Chinese cosmology. The idea also is that neither side of this link, this yin-yang link, is viewed as more fundamental than the other. Right? They're sort of equally fundamental. You can't have one without the other. There's a little bit of one in the other, and so on. So, although it's a bit of a stretch, the dualities that we find in science are actually quite a bit like this. We have the same sort of battling concepts, right? We have hot and cold, big and small, high energy, low energy, finite, infinite, composite, elementary, things that look to be completely opposing characteristics, and yet in some sense we're told, according to these duality symmetries, that they're the same or entangled in a similar kind of way. So there's sort of something quite mysterious about dualities when you view them like this, which makes them quite good material for philosophers of physics to have a look at. So, a nice way, I should have had that up. I forgot I'm pressing my things on here and not on there. Okay, there's the yin-yang symbol. I didn't just go mad, there was a yin-yang symbol there as I was talking about that. So another way of viewing this idea is that we have, so rather than these characteristics like dark and light, for example, what are being related are pairs of theories, right? Theory 1 and theory 2. And this is supposed to be like a symmetry relation. And as we usually find with a symmetry relation, we find that the observable stuff, I'll say for now, we'll go into more detail later on, is the same in both of these theories, but there's supposed to be some difference in ontology, at the ontological level. So basically, two theories are said to be dual when they turn out the same values for observable content, but they stand to one another in a very peculiar way, a very particular way, that one is the reciprocal of the other, always. One is related to the other in terms of this reciprocal relation between a pair of quantities. Okay, and yet these theories can be radically different ontologically speaking. So there's a nice little quote, I'm doing it again, I don't remember to press that one. A nice little quote by John Baez and Urs Schreiber, which I found, which says, and we can agree, I think that an equivalence A equals B is the more interesting, the less A seems to have anything to do with B. So there are a variety of levels of duality that we find, and they we can order them according to a tower of more radical differences, I think. So on the lower level we have things like T dualities that Nick's spoken, I'm sure, in this series about. And on a more radical level, where A has a lot less to do with B, we have things like the ADS-CFT duality, where the theories seem to be utterly different in all possible ways. So here's a standard popular science type description of the ADS-CFT duality. Okay, so this is from Scientific American. This is by Riordan and Zeich. So they say that Maldacena, so this ADS-CFT idea, I'll come to that later on, it's sometimes known as the Maldacena conjecture or duality. So Maldacena has forged a surprising connection between the theory of strings in a warped five-dimensional space and the QCD-like theory of particles that exist on the four-dimensional boundary of that space. Okay, so that's pretty weird. We have a five-dimensional theory that's related by a duality to a four-dimensional theory. Okay, very different. So they say the two theories are mathematically equivalent, even though they appear to describe radically different realms of physics. So I don't think it's so simple as that. One-way dualities are often expressed, but they're not mathematically equivalent in the sense of the same structures. I would say that this is sort of entirely the wrong way around. So in the case of T-dualities, for example, you have non-isometric dual pairs. They're formally very, very different structures, but the idea is they're supposed to be physically the same. So I would have that entirely the other way around. So we might say that, I put it like this, that two theories are mathematically equivalent, even though they... Two theories are physically equivalent, even though they appear to involve radically different mathematics. Seems to be the correct way of describing what a duality is and what's going on in a duality. So we have this strange juxtaposition of equivalence and difference. And what's interesting here in many cases of dualities is that we're supposed to have complete world structures. Right? We're dealing with complete world structures, space-times with entities defined on them, and yet we're saying they appear to be very different mathematically, and somehow they're churning out the same observed values. Okay, so they're two different descriptions of the same thing, but the thing here is a theory. Okay. So this is the root of this strange title of my talk, right? Same but different, or different but same. There's something very weird going on in dualities where they appear to be the same theory in one sense, but they have different ontologies. But in another sense, they appear to be different theories, but they're sort of saying the same thing. It's a very tricky puzzle for philosophers to figure out. And the people around this table right now are probably more than half of the philosophers who've been looking at them, actually, in the world. But they're extremely interesting for these kinds of reasons. Okay. So in a seminar that I think was organized by Nick, which featured Jeff Harvey giving a talk on string theory for philosophers, an audience member said that, well, he said that you said that you're inclined to regard the two sides of a duality as surprisingly different descriptions of a single, i.e. the same reality. Is that the most widespread view amongst practitioners? And then Jeff Harvey, as a string theorist, says, yes, I think the majority do. And I'm in the majority, and I think probably most philosophers, I think, would agree that this is the way to view, this is the correct way to view dualities, right? They're different descriptions of the same underlying reality, right? But there's still, that's weird. There's still a lot more to be said, right? We can agree with Harvey here. It seems like everything's been done, but there's more to be said. It's not just a case of underdetermination and therefore nothing new to philosophers. There are additional interesting complications that we get with dualities. I mean, if these descriptions are all we have to go on, these dual descriptions of these representations, then
it looks like these sorts of dualities are going to compromise our picture of reality. Okay, they're giving us very different physical pictures, and yet they seem to be giving us very different ontological pictures, and yet they're churning out the same values, and yet they seem to be formally linked in this curious way, right? There are direct mappings between the theories. So which one do we choose? We seem to be in a bind. If we go along the lines of Jeff Harvey's idea that really what's happening is we just have two different descriptions, then it looks like what we're doing is we're just changing representation when we go from one duality to another. And then the question is, well, how can a change of representation have such dramatic implications as altering the dimensionality of space-time according to our theories? And I presume we don't want that to really happen. We don't want to be committed to a picture whereby changing a mere representational machinery is altering our ontology to that extent. So I think another important issue that relates to the ontological issues is how we need to figure out how dualities impact on notions of theory individuation, and when we have one theory and when we have two theories. And in fact, what I'll argue later on is that we can use dualities to help us figure out when we have two theories, when we have one theory, and these kinds of things. So, okay, so are dualities special, to start off with? So it's often said that dualities, I mean, we saw it in the popular, the Scientific American article earlier. You often hear people saying that they're sort of deep and profound and special in some way. But as I've already mentioned, it looks like they are very similar to standard underdetermination issues, or if not that, they look at least very similar to symmetries that we find in physics that we're all used to looking at. So let's quickly go through the standard way of thinking about symmetries and gauge and see how dualities relate to this standard picture. So the standard picture is that a symmetry is just a mapping from one state, one solution of a theory to a different state. And it's supposed to be a physically different state. Okay? Symmetries, they map one state to a physically distinct state, and the idea is that they have to preserve the dynamics and the structure and the observables. Okay, so that's a standard way of understanding symmetry. In the case of a gauge symmetry, in this case we have a mapping again, but we're going from some state to the same physical state. Okay, so all that's happening here is we've just got a different representation or realization of the same physical state. So we're not being taken to a new physical state as we are with a standard symmetry. So these transformations are often known as redundancies rather than symmetries, right? Because they just point to the fact that you've got too much mathematical representational machinery in your formulation, right? So states are being overrepresented. In the case of dualities, we have something very, very similar. It looks like a mixture, in fact, of both of these two ideas, symmetry and gauge. What's happening now, rather than having one state mapped to another state, the things being mapped from one to another are theories. So we have one theory, and the duality takes us to a different theory, or is relating that theory to a different theory. And again, the idea is that it's supposed to preserve physical content, the physical observables, the things that you're going to measure in your particle accelerators and these kinds of things. Okay. Now, what's odd about this, and the reason why we think of them as different theories in the first place, is because there are extreme differences of structure. Okay, so this is a quote from a nice paper by Robert Savitt called Duality in Field Theory and Statistical Systems. So as he points out very clearly, a dual theory in general doesn't have the same structure as the original theory. Now, something doesn't have the same structure as the original theory when we're going to think of it as a different theory. It's got entirely different mathematical structures, entirely different degrees of freedom, entirely different dynamics, different action principles. I'll come back to this in a moment. And going back to the Baez and Schreiber quote earlier, the more structural differences that you have, it seems that the more you want to say that these are different theories. Okay, and yet we have this empirical sameness. Right? So it looks like we're sort of in something like the standard underdetermination case, but also not, because there's some nice definite mapping going on. There's this definite symmetry holding the two descriptions together. Right? I mean, so another reason why this doesn't seem like standard underdetermination is because the two pictures tend to be compatible. They sort of link together, again, like the yin-yang diagram. There's not really competing pictures going on here because they're mathematically mappable. I'll just mention a possible link to a standard issue in philosophy of science. I mean, Richard David has mentioned the links, let's see, Keizo has mentioned the links as well, to structural realism, because, I mean, so here's a direct quote from Stephen French. So he points out that, so he says that if the anti-realist can come up with examples of theoretical underdetermination where there are no common structural parts beyond the empirical level, then the structural realist will be scuppered. So given what I've just said, and the quote I just had from Robert Savitt, it looks like these dual pairs do pose a serious challenge to structural realism if this is true, because they do seem to only match up in many cases at the empirical level. The structures are so radically divergent that all you're left with seems to be this equivalence with respect to the observables. So I'll mention later that's not quite true. There are definite preservations of structure across dual pairs, but it's a very strange kind of structure that is left over, a very bare, abstract sort of group structure that's left over. But it's definitely a problem worth looking at, whether there are serious challenges posed to structural realism from dualities, or whether structural realism can cope with them, and maybe even be quite successful in talking about them. So, as I say, if we're adopting this criterion of French's, then it looks like many dual theories are going to be completely different theories. Okay, as I mentioned earlier, they possess different degrees of freedom. One may be about quantum fields, the other's about strings, different dynamics, different gauge symmetries. One could be background independent, the other not background independent. I mean, these are very radical changes. As Holger Lyer put it in one of his papers, distinct theories differ by semantic changes, and there are some very, very significant semantic changes that are going on in dual theories, especially in the case of ADS CFT. So there's a very nice treatment of dualities in this book by Fuchs and Schweigert, which, I don't know, maybe quite a few of you have read, I suppose. It's one of the nicest treatments of dualities. It's very brief, but I think it's bang on, actually. This was written quite a while ago. So they write that, admittedly, there's no clear distinction between the symmetries which relate the states of one and the same theory and those which relate different theories, since in order to distinguish between two possibilities, you have to first specify what you understand by theory. So the choice of what you mean by theory can change with time. So you might think at one time of a family of models at different parameter values, and in another case as a single model at fixed values. So I think what this shows is that we need to be especially flexible when it comes to interpretive matters regarding ontology in the case of dual theories. I think Keizo I had a quick scan at the paper of Matsubara and Smink, and I think it seems to be making the same case, that there needs to be some sort of flexibility with respect to the ontologies of the dual pictures, and I think you call it scaffolding in that paper. Is that right?
Well, the scaffolding is kind of before we make the interpretation.
Right. Mm-hmm. So they go on to say, duality implies the existence of two or more descriptions of the same theory. This implies that it's possible to get more information out of a theory that's possible using a single description. So this goes back to the quote I gave at the beginning with Jeff Harvey. It's the same idea, and I think this is exactly the right idea. But again, it still leaves much unsaid, philosophically speaking, about which description, if any, we should be realists about, how we're supposed to be realists about situations involving dualities. It seems to be troubling for standard realist and structural realist accounts alike, since the structures, again, are seeming very, very different. So the way I like to think about dualities is via this sort of diagram. So you have a pair of theories related by a duality map, which generally takes the form of this. It's basically a modular group that serves as your duality map. You're mapping a quantity to the reciprocal of that quantity. The idea is, as well, you can calculate the same physical quantities in either representation. It's just that it's going to be easier in one than in the other in many cases, sometimes very intractable in one. And the way I like to view it is that this dual pair they are representations, or descriptions of a different theory. This is what is basically being said in the previous quote. They're describing one and the same thing. Now, what that one and the same thing is sometimes up for grabs. Sometimes we know what that one and the same thing is, right? That they are both describing this additional theory. Sometimes we don't, and it's a matter of conjecture. In the case of M theory or ADSC of T, it's not completely settled. So going back to the original simplified idea of a duality, I think in order to make sense of what's going on ontologically with dualities, we can't say that they are ontologically distinct, okay, while they're identical in terms of the observables. I think we have to say that they're also ontologically equivalent as well at the same time. And the differences are coming about from non-physical differences to do with the representation. The reason we're getting these dual pictures is because we have redundancy appearing in the theories. And when you get rid of that redundancy, what you end up with is ontologically one and the same content, one and the same physical picture. So let's go through some examples and see this in action. It's very awkward doing two at the same time. So this is Kumran Vatha. He writes very well on dualities, I think, for philosophers. Very clear. So he writes that one of the most interesting aspects of string theory is that strings moving on one manifold may behave identically with strings moving on a different manifold. Any pair of manifolds, M1 and M2, which behave in this way are called mirror pairs. Of course, this would be a trivial duality if M1 and M2 are isomorphic Riemannian manifolds. Again, that goes back to the Baez and Schreiber quote. We want these things to be as different as possible and yet equivalent. The interesting dualities arise when M1 and M2 are distinctly Mannian manifolds. In some cases, M1 and M2 are topologically the same, but in some cases they're even distinct topologically. Again, highlighting the radical differences in structure and the reasons why we want to say that there are two theories in the case of a duality and not one. So, now the example he's alluding to is this mirror duality. T-duality, which I mentioned earlier, isn't just an example of mirror duality. Mirror duality is a generalization of T-duality. So what's going on in this case is that we have, I should say first that in string theory, you probably all know this. I don't know who's over there either, but I'm sure everybody knows this. But in string theory, you have to use certain compact spaces because the theory only makes sense in 10 dimensions in certain string theories. So you have to get rid of 6 of those dimensions. And to do that, you compactify. So you make the strings wrap around these tiny dimensions and they're so small that you can't see them, and space looks effectively four-dimensional. The simplest way of thinking about this is just to compactify, imagine compactifying a string on just a circle. And when you do this, you find what's called you find T-duality. So we have a pair of string theories. Here the two sides are T and T-dual. These will be a pair of string theories. Right, so for example, there's various names associated with string theories. So we have that E8 times E8 on a circle, compactified on a circle of radius r, is going to be dual, equivalent, give you the same physical results in measurements and so on, as SO32 on 1 over r. It doesn't matter what those E8s and SOs are. All that matters is that you've got what are considered to be two distinct string theories with different degrees of freedom, different types of string, that seem to be equivalent when they're compactified, wrapped around spaces, circles of very, very different sizes. One where you've got a circle of size r, and the other way you've got a circle of size 1 over r. And obviously if r is a million meters, then your 1 over r is going to be 1 over a million meters, a millionth of that size. These should be radically, radically different things. A really, really huge circle, a string on a really huge circle, and a string on a ridiculously tiny circle seem to be very different things physically. And yet we end up with an equivalent in terms of what the string theory says is going on in that universe. Any measurements you make using strings to try and determine what's going on and what kind of space you're in, you're going to get the same values regardless. So you can't use measurements using strings to determine whether you're in R or 1 over R. Now, going back to this little downward direction where you have this other theory of which these are both descriptions with redundancies, what we do is, well, we're considering string theory as being defined on a space of these loops here. And what you can do is take what's called an orbifold of circles of radius r. So not any old circles so we identify circles r and 1 over r for all r, basically. Now what this means is that you basically end up with a smaller space of physical possibilities. You've hacked away all radii with values less than 1, essentially, because of this 1 over r. So strictly speaking, to represent everything that's going on, you only need real numbers bigger than 1 to represent everything.
Or less than 1.
Or less than 1, one or the other, right? Either will do. Right? Point being, you've got, again, a lot of redundant structure in there that you don't need, that isn't doing any representational work, any physical work, or picking out any physical differences. Okay, so this orbifold, just for completeness, is this thing here, R over this discrete group, Z2. Okay. So how are we supposed to make sense of this? You probably have seen all of this before with Nick's talks. I do apologise.
Well, I don't know if everyone here has, and then people will watch the video later who may not have done anyway.
Right.
So.
Okay. So.
It's so cool. I never tire of it. So.
Okay, so you. So to get into the idea of how T-duality works, you can think about just the quantum mechanics of a point particle rather than a string on a circle, right, on this little compact space. So your space of states here is going to consist of square integrable functions on the space of circles. Right, so your space is going to be S1 rather than R. Now the difference is with strings is that they can wind as well. So you've got two different types of degrees of freedom. Right? A particle can just move around, a string can move around and wind around. In quantum mechanics, the smaller the radius, the greater the winding energy, more wraps of the string. But there's no quantum mechanical particle version of this. Okay, so we've got these additional kinds of motion here. We can move the string can move around, but it can also wrap around. Okay, so these normal motions are called ordinary Kaluza-Klein motion, just where you're moving around a compact dimension. And then these other types of motion are called winding, or these other types of mode are called winding modes. And it turns out that your string energy spectrum, the thing that you're going to calculate, is a combination of both kinds of mode, right? They're both needed to compute your energy spectrum. Okay. So, it's quite easy to understand how the dualities work in this case. We know that when we shrink our space, the string is going to be more confined, so it's probing smaller distances, and energy and distance are inversely proportional in quantum mechanics. And likewise, a larger radius is going to mean a greater winding energy of the string, because obviously your string is getting stretched around it, so there's more energy, because energy is just energy per unit length of string. So the more unit length of string you have, the more energy you have. So you've got one that shrinks as the other one grows. They're basically just doing a balancing act. So when your radii are switched, the winding modes and these ordinary Kaluza-Klein modes are switched as well in terms of values. Okay, so it's basically just this reciprocal balancing act. And something similar, although much more complex, happens in pretty much all of the other dualities, where we have this exactly this balancing act because of the reciprocal nature of the relation. Okay, so we end up with this equivalence where very different spaces, R and 1 over R, are going to be indistinguishable according to the string theory, because of the way the strings move and these additional winding modes that you get in string theory. So their total energy will match. Okay, so the two theories that you get on these two different spaces are basically physically indistinguishable, but geometrically very, very distinct. So no physical processes can distinguish what look like very geometrically distinct entities, spaces. And as I said earlier, what you generally do with cases like this is, when you've got this sort of redundancy, is you take the equivalence class, right? So you take the orbits of your circles or your tori or toruses by a discrete group and you get rid of the redundancy. Right, a nice way of thinking about this, there's a mathematical musicologist called Dmitry Tomochko at Princeton who talks about orbifolds using piano keyboards. So the idea is you've got, you can imagine going from C to C, but then it repeats, and you've got another C, and it repeats, and you've got another C. So in terms of harmony, all that matters is that you've got a C. It doesn't matter whether it's this C or this C or this C. So what you do is you identify all of your octaves, and you take the equivalence class of all of those. Because musicologically speaking, all that matters is that this is a C, and you can do the same with chords and say that C major chord is just your C, E, and a G, but it doesn't matter which C, E, and G it is. It could be any of the E, Cs, and Gs. So you collapse them all, and you take the equivalence class of all those chords, and that's your new object, and that's basically an orbifold. Now this is just like gauge freedom so far, right? And we can deal, it looks like we're dealing with it in the same way as gauge freedom. And most people do actually agree that cases of T-duality, cases like this, are basically just examples of gauge symmetries. Now, it gets a little bit more, I'm not going to go through this, but it gets a little bit more complicated in the examples that Vaffer was mentioning, the mirror manifolds, where what you're doing, rather than looking at theories on different sizes of compact space, you're looking at theories on where you're swapping the shape and the complex structure of the manifolds and looking at the string theories on there, but you find the same thing. What look like now even more radically distinct theories, where you've got radically distinct spaces that aren't even isometric anymore. You still have the situation where if you're doing experiments with strings, you can't figure out which space you're in, right? This one or the dual one where you've altered its size and shape. Complex structure, sorry. So it looks like, whoops, I've done it again. I've got to remember, that is the keyboard I'm pressing, not that one. Okay. So we find that distinct spacetimes are string-wise indistinguishable. Right? If you throw particles in there, you can distinguish them. If you've just got a universe with strings, you're not going to be able to distinguish whether you're in a space with in a universe with one kind of space or the dual kind of space. Now, so I've put spacetimes in scare quotes here because we've sort of been jumping in and giving it a physical interpretation, these structures, without thinking about it properly first. So I think the point about dualities is that the entities that we're claiming are dual and that we're calling spacetime are not really properly functioning as spacetime. They're gauge degrees of freedom. If anything, it's going to be the orbifold that represents the invariant object that's going to be the physical stuff that's going to somehow be your spacetime. Right, where we've eliminated the redundant machinery of circles. So your compact radius isn't, as it sounds, isn't a fundamental property of string theory. I think it's a gauge degree of freedom, just like other gauge degrees of freedom, like coordinates in general relativity. So, I mean, this is exactly the same sort of thing we find in the whole argument, right? According to standard orthodoxy now, all the problems of the whole argument happened because we jumped in too early and interpreted the manifold, or the manifold and metric, as the thing that was going to represent spacetime, and it got us into trouble because the theory can't say which spacetime it is and which point this field is at. But that was a problem. It wasn't really a physical structure, so we need to, in that approach, go to the geometry rather than the metric. Right? We take the equivalence class of metrics, and then that's our physical structure. And in the same way, in the case of the T-dualities and these mirror dualities, we do exactly the same thing. And it's been done in the case of T-duality, where you can get this underlying theory where you've got an equivalence class, the orbifold, right, which has eliminated the redundancies with looking at string theory on circles. And you can have genuine string theories on these things, these orbifolds. Right, there's a paper from 1985, a famous paper by Vaffer and Witten and Dixon, and I can't remember the other person, where they do exactly this. They show how you can do this. You can construct string theories on these strange orbit manifolds, right, where you've eliminated the symmetry using this discrete group. Okay, so it looks like, and I think it is in very, very many ways, this is just the whole argument again. Right, there's a question about ontological commitment here that seems to be identical. Do we take the symmetry to point to the reality of the orbifold, or do we take each of the other pictures to be realistically depicting some possibilities as well? Right, we can do that. We can play that game in general relativity as well and say, look, no, we're going to say that these are really distinct physical possibilities. It's just that the theory can't say which one it is. Or you can do something like say there is one true, I think you've mentioned this, there is one, Nick, there is one true representation, one true radius, and the rest are all false. It's just that we don't know which one that is and we can't epistemically access it or whatever. So you have all of the same interpretive options with these dualities, certainly in the case of T-duality, as you do with the whole argument. And the reason for that is, I think, because it is just another case of the same sort of symmetry argument, the gauge symmetry. Okay, so just as we do with the whole argument, then it seems that we've got a standard ready-made solution for all our duality problems. Okay, we just orbifold everything. When we find a duality, we take something like the orbifold, the equivalence class. All right, so far this is just gauge again. Right, having these indistinguishable bits of structure doesn't serve any physical role, so we should eliminate it. It seems to work okay, but there's still a problem in some cases, not so much in the T-duality case, but there's still a problem of saying what kind of thing this resulting structure is that you've got, right, with its lack of redundancy. Okay, so there are, it seems to get a bit more, what's that? Oh, crap. So used to doing it on there. So it seems to work okay for T-duality and mirror dualities in general, but when it comes to more complex examples of duality, that approach doesn't seem to work quite so well. It seems to be a little more strained. So there's another duality known as S-duality, which again is basically, it is more of the same. You have a pair of string theories or maybe quantum field theories, and the S-duality relation refers to the fact that you are mapping one coupling constant of one strength to 1 over that, the value of that coupling constant. And so again, we've got this reciprocal relation. It's basically a modular function, so the modular group appears all over these dualities. In this case, we're not dealing with radii, we're dealing with coupling strengths, and we find, once again, that theories that should be very different, theories with very different types of object, different types of strings, are being related, they're being found to be equivalent, right? They make the same predictions. Their symmetries, their physical symmetries are the same, and so on. You can also find this same duality, symmetry, S-duality, on 2D Ising models, lattice models, where what you're doing is you're switching, instead of using this G coupling constant, you're switching a temperature, the theory at one temperature with 1 over that temperature, and you find the same result. Right? You find that your correlation functions, the things that you're going to predict, are identical, your symmetries are identical. Now, it's no accident that there's conformal invariance in those examples. The ADS-CFT duality is an example a bit like this. I did have a very long description of the ADS-CFT duality, but I've taken it out because this was 3.5 Einsteins. I thought I'd best eliminate it. So I'll just say a few brief things about this. Again, this is probably, I think this is acknowledged to be the most bizarre of the dualities, for the reasons that our A and B, our two dual theories, are about as different as it's possible for a pair of theories to be on the surface, prima facie. So in this case, we would have on one side a string theory in 10 dimensions, or 5 cross 5 in this case. And on the other side, we would have a non-string theory. We'd have a gauge theory, quantum field theory, in 4 dimensions. That's why it looks so bizarre, where we've got a gravitational theory, a string theory. It's gravitational. All string theories are gravitational theories. And we have a non-gravitational theory, the gauge theory. String theory has diffeomorphism invariance. The gauge theory doesn't have diffeomorphism invariance. String theory is 10-dimensional. The gauge theory is 4-dimensional. Structurally, there's not a lot that you can find holding these two pictures together, and yet, according to the conjecture, because it's, so far as I know, it still hasn't been proved, although it's near enough proved. Again, we get the same equivalence of observable spectra. In this case, as with the S-dual case, there's something a little bit bizarre about this idea that they are representations or descriptions of some other same thing, some other underlying theory or deeper description. And the idea is that there's supposed to be some M theory, some theory out of which all of the other string theories come as limits. I haven't said much about limits. I'm sure Keizo will say something about limits when he gives his next talk to this group. Because again, I saw that there was quite a bit about looking at limits, at dualities as limiting theories and treating them as sort of effective ontologies, which is quite a nice idea. So this is a kind of S-duality in this case. When the gravitational description is in effect on one side, then your dual gauge theory will be strongly coupled, and vice versa. Right, so when one is strongly coupled and hence very hard to deal with mathematically in making predictions, the other one will be weakly coupled, and this is why this is such a this is often used as a tool, because you can make predictions about things that you couldn't otherwise make predictions about, because your little weak coupled theory is letting you talk about things in the strongly coupled theory, which is usually out of bounds mathematically. It's intractable. So you can do weird things like look at black holes to study quark gluon plasmas and all these kinds of things. Okay, now this is a very bizarre jump now, I need to remember how I got to this. So now in the case of this ADS-CFT duality, the physicists speak explicitly about a dictionary relating your theoretical terms in one theory to the theoretical terms of another theory. So you can speak quite explicitly about your duality mapping. So there are all sorts of interesting associations where, for example, your spatial direction on one side is going to be equivalent to an energy, your radial dimension is going to be equivalent to an energy scale in the other theory. So that you're sort of defining or associating one particular theoretical concept or piece of the ontology with another in the other theory, which looks very, very different. Now again, I will just say, just to really emphasize, in this duality we've reached utterly insane levels of difference, basically. Right? If you couldn't really find a pair of more different theories if you tried. You would never think that these were the same theory. And yet we have this duality mapping relating them. When Maldacena devised this, he built it up using this duality mapping and built the other theory, one theory from the other theory. And we have the same result that we're getting this, the same physical predictions again. So, so do we have two theories or one or none here? So there was a nice paper recently by Kevin Coffey in BJPS, paper about theoretical equivalence, and he writes at one place, theoretical equivalence is a function of interpretation. It's a relation between completely interpreted formulations. Now, I think the reason why these are so confusing, these dualities, and especially things like the ADS-CFT duality, is that we are interpreting the dual theories as... Oh, hello. Is that we are... Oh, what happened?
I don't know what happened to...
Where did I go?
Where did Keynote go?
I don't know. There we go.
Hold on. Chris? Chris?
I think you turned him... Maybe.
No, I am muted.
Yes.
Do you have the slides okay at the moment?
What?
Did you lose the slides for a minute?
Yes.
But it's okay now?
Yes.
Okay.
Okay, so I was asking, are there two theories or one or none in the case of ADS, CFT, and other dualities like that? And there was the quote from Kevin Coffey. Okay, so theoretical equivalence is a function of interpretation. It's a relation between completely interpreted formulations. And I think what is going on when we're getting confused about dualities is that we're taking the two sides, each of the dual pair, to be a completely interpreted formulation in its own right. That would be basically the same as taking your various, in the case of the whole argument, your various metrics laid differently over the manifold as completely interpreted formulations. You've got a full picture there, and you've got another full picture there. I think what we have to do, and I think dualities are pointing to this, is that we don't interpret dual theories literally and directly. They're telling us to take an equivalence class to figure out what is the physical structure and what is representational redundancy, just as happens in the case of the whole argument. Right? So the existence of a duality is a very helpful thing, just like gauge symmetry is a very helpful thing. Gauge symmetry, we overload mathematical form representation. There's too much. We hack out the redundancy, and it gets us to the physical structure, the intrinsic structure. I think dualities act exactly like this. They point us to unphysical structure, and they also point us to a description-dependent structure, I should say. What I think of is a sort of generalization of gauge. But they also point to some invariant structure, right? There always is going to be invariant structure because there's always this mapping between dual theories, holding them together. That's why they're dual theories. That's how this thing works. So dual pairs are going to allow us to identify unphysical and physical structure. So I think they're a tool, but I think that tool is basically just like gauge symmetry. What's slightly bizarre, especially in the case of ADS-CFT, is that and again this goes back to both the Stephen French quote and the Urs Schreiber John Byers quote, there's so little shared in the end that the only thing that seems to be shared is this global symmetry group. They both have the same symmetry group. But it seems strange to say that you would be committed to that. So I think until you have a deeper theory that explains the existence of this particular symmetry group and why we have that particular symmetry group and that it's based on this particular symmetry group, I don't think it's possible to say that you can give a reasonable physical interpretation of the theory. In the case of T-duality, you can, because you know the structure is this orbifold and you have strings on an orbifold. That's why you were getting the particular representational redundancy you were getting, because you were adding in, you were treating all of the members of the equivalence class that you had as separate pictures in their own right. So we know how it's all working. In the case of ADS CFT, we might someday get a theory that does the same thing, just like the strings on orbifolds case does. But at the moment, I don't think it's even possible to give a decent interpretation of what's going on in the case of ADS CFT and what it says the world will be like. So, but I do think it points us, and I do think in every single case where we have a duality, that it points to some deeper, I don't know whether I want to say deeper, it points to some more intrinsic theoretical picture of which your two sides, ADS, CFT, whatever, string theory on one side, string theory on the other, provide representations just with different degrees of freedom, like a change of representation, change of variables, for example. So in this case, I think we should be very much against model literalism, just like we're supposed to be in the case of the whole argument. We shouldn't provide literal interpretations in dualistic scenarios, because there's what they're pointing to is an incompleteness in the description. Okay, I think I'll leave it there actually. 45 minutes.
Okay.
There you go. That's the summary.
Okay. Good on talking.
Mm.
Okay, thank you. All right, give me like 2 seconds to get.
Okay. Questions here?
Thanks, Steve. So, when you say you're against model literalism, can you hear me?
Yes.
Yeah.
When you say you're against model literalism, how do you, since it's incomplete descriptions, what do you say then with respect to applied ADS-CFT context? Because in those cases, it doesn't seem to be incomplete descriptions.
Well, I would say in that case, that's a good question. I'd say in that case it's then legitimate. I mean, you have a good reason, in principle reason, to latch a particular physical. Actually, no, I think about it. The black hole description in those cases clearly isn't meant to be taken literally. I mean, there is no model literalism in those, for example, the quark gluon plasmas I assume you're referring to, where you're using black holes. You're not being literal about the black hole interpretation there. You're using it as a tool. You're not giving it a physical interpretation as such, in terms of black holes.
Yes, in the case of black holes, it's the one side of the duality, but if you also consider, for instance, those condensed matter systems, there you can be literal about what side of the duality.
Okay, but
right? So if you're looking at phase transitions where you have conformal invariance.
okay, in that case, I would say that you have an in-principle reason to sort of, I don't know what the word would be, to saturate that side of the duality with an interpretation. You are latching it on for good principled reasons. But I don't say, I mean, in the case where you're dealing with it in a more fundamental way, I don't see how you can do the same maneuver. I mean, the applied case does seem to be very, very different. I mean, you could do it with... I suppose you could do it even in the general relativity case, where you imagine fixing some particular gauge in some way, fixing a set of coordinates, and then you can say, yes, look, there we go. I mean, it would be like fixing a gauge, I suppose. Would be sort of the equivalent idea. You fix a set of coordinates, and then now this is the set of coordinates. This really is.
But is it on now? Yeah. But whenever you would actually apply the ADS-CFT to any concrete context, then you would latch on one side. So you would you would say you always gauge fix in those circumstances. Is that right?
I think I would say yes, but I need to think about that further, actually. But I think I would say yes, whenever you're latching it on to an actual physical system like that. I'd need to think about that further. I suppose you could do it again in the case of the T-duality, where you know that there's a particular size. I don't know. I need to think about that further, actually.
Thanks.
Yeah, but I think it would be gauge fixing is my initial reaction. But yeah, okay, thanks.
Do you guys have questions?
Yeah. I was thinking, even though I agree with the view you're presenting, but I wonder how the people who prefer the other view, the ones who would kind of insist on seeing this as some kind of undetermination, I kind of think that you mainly argue for your point by saying you could do the same thing as we always do in gauge and whole argument, and also one more thing, this kind of complementarity thing, that we kind of get more information by having both of these things. And these are kind of reasons to, or at least reasons to see that view as viable. And I also think it's the most attractive, but can we go farther to see kind of an argument against the one who want to take the other view, like put that in a harder way, or is it more like elucidating the possibility of this view, which I share as well, but I mean, how far can we go to kind of attack the other view? And I don't see so much of that. It's more kind of, I'm a little bit vague, but I think you're,
That's it.
I mean, in the sense,
I think the idea that they're not competing is an argument against,
okay,
whereas the other one is more of a plausibility argument. So I think they're different kinds.
yeah,
And, well, again, you could do the same in the whole argument the other way and just stick and resist the idea and call that underdetermination as well. I mean, it's just not a very sensible approach, I don't think.
but that kind of complementarity thing, even why is that? I mean, I can see to some extent why that is an argument for, but would you just kind of spell that out more, why that is a strong argument for taking this view?
It's not a particularly, for this view.
Yeah.
That's supposed to be an argument, as I said, against the idea that it's a case of standard underdetermination.
Okay.
You know, I mean, so the idea is in the Poincaré disk example, you don't really get more information, right, in those cases by thinking in terms of contraction forces or curved spacetime.
Yeah.
You're not gaining anything. One might be easier to use. There's that. But there's no additional information.
Couldn't the one who really persists on the other side say that it's more kind of a practical calculational problem rather than something else?
They could, but then I would expect at least that they could come up with something akin, or that looks like it could do the same job in a standard, straightforward underdetermination case.
Okay.
Make it.
Good.
Can I read a question from Johan? He's getting blown off in these situations, so I wanted to give him a turn. I think it's partly what you maybe kind of asking then as well. So he says he feels that you partly that in what you're doing there's a typography of dualities in the following sense. So T-dualities are really similar to the whole argument and gauge degrees of freedom, but you're saying S-duality and ADS-CFT, well, he says, are more confusing than that, but they're sort of in a, I mean, you want to think of them in a different category?
No, not at all, no.
So Dean suggests that S-dualities and ADS-CFT are rather different. Is this right, or did I misinterpret Dean's point?
No, misinterpreted. I probably said it wrong. I mean, the point is they look like they're very different, and people seem to think that they're very different, and people are willing to say that T-dual theories are just standard examples of gauge, but not these other ones, as if there's something radically different distinguishing them. But it's the same kind of modular group that's grounding those S-dualities as with the T-dualities. It's just that they are more complex, but it's the same principle. And the main problem is that where in the case of T-dualities, you have this nice intrinsic picture to work with. You don't get those, so far as I know, in the S-dual cases. There's no nice intrinsic picture that you can draw upon and say, look, this is just like the whole argument all over again. But again, it's not actually, Keizo's completely right. It's not really you've mentioned this before, an argument for it. It's just, it's more of it seems very plausible to me, given the other analogies holding between these two types of duality, that the same thing would hold, that there would be an intrinsic description, that there has to be an intrinsic description, of which the two S-dual theories would then be representations of limits.
So it's a quantitative difference rather than a qualitative difference.
Yeah,
I mean, quite an extreme quantitative difference.
Yeah, it's exactly
like that.
Yeah.
Actually, do you mind if I sort of follow up with this a little bit? And this is actually something that the second question that Johan had as well, to do with the global symmetry group, and maybe you could say a little more than that about that. But I mean, I was thinking about the existence of the dictionary, I mean, gives you some access for saying maybe some more specific things that they have in common. I mean, they both have in common this this parameter, which looks like a radius in one and looks like a renormalization scale in the other. So there's something more you can have. And I'm thinking about the recent paper with, I don't know, Jeremy and Sebastian, talking about actually arguing against, I think, Vaffa, right? You know, this paper that the diffeomorphism symmetries really do show up as gauge symmetries in the. So the conventional wisdom was that you can't kind of compare them, but they have a recent paper in studies showing, at least in some cases, that the symmetries really are that you're looking at are the same thing.
Oh, so they've added another entry to the dictionary, you mean?
Yeah, but quite a sort of one that goes against conventional wisdom.
Well, that's even better for my case, obviously.
So it's sort of like it's not as dire maybe as just the global symmetry group or something.
Well, that's a fair point. I mean, obviously, the things that you are mapping from one to the other. The reason I mentioned the global symmetry group is because that is sort of like absolute shared structure between them, right? They have that one and the same symmetry group, whereas the dictionary is a different sort of thing, right? The things on the two sides of the dictionary are basically just like your ADS-CFT all over again, right? So you've got a thing that's very different from this thing, right? And you're just saying you can find mappings, but still, if you're confused about the ADS-CFT duality, finding this other little pair of sub-quantities that are also dual in this funny way isn't really going to help you get your head around it. So it's nice that there's a duality, these mappings. Obviously, that's just sort of like a necessary condition that there will be these things if you have a duality. If you don't get them, it's not a duality in the first place, so you've got to expect them. It doesn't take away the confusion about how it's happening, that these very different things are being able to do this and then generate exactly the same physical quantities. And as I say, the global symmetry group really is the only thing that is genuinely the same. so far as I know.
At that ontological level, of course, they have all the observable stuff.
And well, yes, right, that as well.
Yeah. Did you want to go?
Sure. So in Duality, you said that the orbifold structure is somehow part of the underlying theory. But sometimes people say, as you said yourself, that M theory is underlying these duality.
Oh,
So I was wondering whether you know any work has been done connecting the orbifold structure theory, or if there's any connection.
oh well. I mean, so when you see the little web of theories that you always see,
Yeah.
right, of M theory with the various limits of string theory, obviously your orbifold structure, T dualities are sort of encoded in this particular diagram, right? You see like little links from one theory to the other, and it says, you know, these are T dual in this way. So sort of they're going to share, they're T dual because they share the same orbifold structure.
Yeah.
I don't know whether anybody's done anything deeper to show how these orbifold structures emerge from something else and are themselves sort of, you know, emergent structures at this some particular low energy limit or whatever.
But presumably some string theorists might ultimately hope that
Presumably it would have to happen.
like that.
Yeah. But it would be, I don't know how it would work, but it would be very interesting, I'm sure, to see how that emerged. I mean, it's basically another example that Nick could study on the emergence of spacetime. This is very different. It would be a very different kind of emergence, an orbifold emerging from something. I mean, maybe some of the stuff that Brian Greene and Morrison and Plesser did on topology transitions and topology change would go into that.
Can I follow up on that orbifold point as well? So there's something I didn't quite understand, and I should probably know the paper, the Witten and Baffer and Dixon paper that you mentioned. So I don't quite understand. So, I mean, the orbifold, the way you described it, is the space of spaces, not a space itself, right?
No, but it is a certain kind of space. But it's got singularities. But the whole point of that paper was to show that the strings don't care about the singularities. Point particles would, and that's how they would distinguish the different types of space. They wouldn't be able to propagate. You can't get a consistent theory of point particles on these orbifolds, but you can with strings because they don't sense.
But the way you the way you described it is you sort of imagine the space of circles of all different radii, and then sort of quotient out by the reciprocal. But that's the first thing you start with. Each circle is a physical space, and the space of circles is a space of physical spaces. So the orbifold doesn't seem to be a thing, you know, like your torus, right? You've got the string
but it is
kind of moving around on the torus. The strings aren't moving around on the orbifold if it's there's a fixed radius.
No, but the strange thing is, in that paper, that's exactly what you can do. It's a very odd space. You've got strange identifications. You've got singularities, right? The strings are insensitive to the singularities.
Right.
So you can get a consistent dynamics, string dynamics on an orbifold, as is shown in that particular paper.
So I guess I'm asking you to explain the paper more to me at this point.
I don't actually.
Well, just at a very broad conceptual level. So I'm thinking, okay, so I've got T duality, and okay, so the observables are insensitive to whether the radius is R or 1 over R.
You're supposed to think of it
R or R prime.
I think in the diagram you're supposed to think of it as a kind of lattice of identifications. I think that's the sort of diagram they have.
But this, yeah. So I think I understand what space you're talking about. That's not. It's what it actually represents. I'm kind of confused about, right? Because in T duality, the observables will tell you, right? They won't tell you whether the radius is R or 1 over R, but you can measure and figure out whether it's R prime or 1 over, or whether it's R or R prime, equivalently R 1 over R or 1 over R prime. It's not like you can't have there's not a duality between all radii, just reciprocal radii. But the orbifold seems to contain all the radii, so I don't.
You've got to remember that conformal symmetry is playing a huge role in here. As soon as you're inserting things and saying we're going to measure radii, presumably you're going to be breaking conformal invariance, and the T-duality is going to break down. It's a strange sort of...
But the conformal symmetries of the worldsheet, not of the target space. Okay, maybe it's
yeah, well, I kind of agree with you, because I think that the orbifold you're talking about there is describing, it's like what your point is basically, the orbifold you described there is not in itself the relevant target space. It's or the relevant, it's kind of a space of possible solutions rather than...
No. It provides a consistent background for string propagation.
You could have that as well, but that's kind of a different question from this one. I agree that you can have orbifolds and they play the role of target spaces in string theory in many cases. What I don't agree with is that in this case, I agree with the thing that we should identify R and 1 over R as representing the same physical situation. And then that the orbifold we get by identifying them classify the space of those relevant solutions. I think isn't that the same thing as that's what Nick said, right? So the orbifold you construct there plays an important role for kind of classifying the relevant physically different solutions, but I can see how that in this specific case represent the target space, even though I know there are other cases where we can have an orbifold as the target space.
I mean, okay, so how would this...
I don't know, you can... I
Yeah,
think you can decline to explain that
sure.
at this point, and we'll
Maybe-
talk about your
maybe I
paper instead,
misunderstand
because I haven't read it, so I
Yeah.
don't quite know.
Well, I mean, how would the same situation work in the case of general relativity? I mean, could we not say the same thing? I mean, there again, we're dealing with... we take the equivalence case, we're dealing with superspace. But you could say the same thing, that it just looks like a configuration space of all these possible 3 geometries when you take an equivalence class.
But they're indistinguishable, right? The different radii aren't indistinguishable.
No, they are indistinguishable according to string theory if you've only got strings.
Only the reciprocals are really indistinguishable.
Oh, I see what you mean. Right, okay.
So, right, I can tell whether the string is, whether the radius is 1 meter or 10 meters. Just not whether it's about 10 or 10th, right?
Yeah.
But I don't know, maybe while you're here, I'll look at the paper and we can talk some more. And
Okay, that's a different point. Yeah.
give our Swiss colleagues some more. I don't know, unless you want to say something.
No, I need to think about it, because I thought you were asking an entirely different question, actually, but I see what you're saying now. So, yeah, it's almost like this is like a single shot case where you have an orbifold just for this pair of radii, and you have to forget every other radii exists.
Yeah, is that what they're doing? Yeah, I don't know.
Possibly, but I think that's how I would have to answer that for it to make any sense.
Okay.
That picture.
Okay.
Geneva,
you have some more questions over there?
Hey, thanks, Lee. So I'm not quite clear about the effect of structural realism in this context, and it seems to me that at least one strange option is still available in the context of ADS CFT. That is what is sometimes called group theoretic realism, or basically what Kantorovich had in mind when he was suggesting that it's really the symmetry groups which are fundamental stuff and everything else is derivative on that. Would you say that, at least given the current state of things, that's something like an option for ontic structural realism of some shape?
Yes, I think I've written that in a paper somewhere, I think. But I mean, the problem is the structure. What you're left with is a very, very flimsy kind of structure in this case. It's hard to make physical sense of saying we are committed to this group structure. It's I don't know. There's a possible case for the structural realist because this is shared group structure between the dual pictures, and it's all that there is. I mean, you could possibly rescue structural realism with it, yes, but it would be quite a bizarre version of structural realism.
Yes, follow up. At least in the Kantorovich sense, the symmetries he was considering, from them you can both, through the reproducible representations, get the particles and the dynamics. This is far from trivial in the global symmetry structure that is left here, right?
Well, suppose you'd end up with two ways of... Well, the problem is you've got two ways of breaking it down in this case, right, which are giving you your Yang-Mills and your string theory. So you're faced with exactly... It looks like you're... Well, if you're a standard realist, I suppose you'd be faced with the problem. I'm not sure if you are faced with the problem if you're a structural realist, the fact that this breaks down into two separate... You can decompose it in two different ways. Right, the bosonic subgroup or the superconformal symmetries of your n=4 theory. I'm not sure, does that pose any particular problems for structural realism, the fact that you can do that? I'm not sure that it does. I mean, the group structure is still shared. The same deep group structure is still shared between them, this PSU 224.
Sorry, I couldn't hear the last part.
Oh, I was just saying that I'm not sure how that would be a problem for the group structural realist. Anyway, the fact that you can break the supergroup down into these two different subgroups. Is that what you were saying?
So no, I thought you were saying the common structure is the global symmetry that you were mentioning.
Yeah.
And the question is whether the global symmetry is sufficient to get everything interesting in terms of particles and dynamics. Because for the group structuralist position to be viable, you have to be able to derive quite a lot out of the symmetry only, of the symmetry group only. And
well, yes,
that the global symmetry group.
Well, this is what I was saying. So I think you can, but the thing is, you end up getting two different subgroups out. You end up getting the isometry group of the string theory, right? The ADS5 times S5, and you get the superconformal symmetries.
Okay, I didn't hear that. Okay, I didn't.
And then from that, obviously, you get all of your dynamics. So you could, is the answer.
Cool.
That's actually quite cool.
Okay, I have another question. Are there more questions there? Chris, you've been pretty quiet today. So my question was, I guess you want to point to the existence of some underlying theory, some correct set of, degrees of freedom and whatever, some dynamics, or whatever for them. So do you think? Why did dualities give you any sort of independent grounds for thinking that there is such a theory? I mean, string theory, these are all perturbation theories pretty much. So, it seems like there has to be something underlying for which, so we have those reasons for thinking that's the underlying theory. Do you think dualities give us additional reasons for thinking that? And why?
Oh, it's the basic idea that you have.
It's possible, but
I can't see how you can make sense of dualities without it. I mean, you always have the symmetry mapping. And when you've always got the symmetry mapping, you can always divide out by this discrete group, right, by your modular group. You can always do that. So there's always going to be some intrinsic structure. The question is whether there's there then needs to be a theory with its own degrees of freedom, which has that symmetry group, which has this intrinsic structure, right, as its structure. Does that make sense?
Well, the alternative would be, I guess, one of the duals is right, and it's just a coincidence that there's this other mathematical other mathematical formalism that is dual to it. I suppose that would be the alternative. So maybe the answer is, well cases like that in the past.
But that, right, and then you're into whole argument territory, and you can say, well, in that case, we've got a bit of a problem because our theory can't determine which of them is true. It might be one of them, and we'll never know, and there's an epistemic problem going on here. It's almost like not being able to detect absolute velocities or something like that.
Right.
So it could be the case, but it's not very nice if it is the case.
Yeah, okay. Good.
I mean, and that doesn't get around the fact that if you do have that symmetry group, you can always quotient by it.
I have a question from Josh Norton. I'm not going to read the whole thing, I'm afraid, Josh. Assume he can still hear. Basically, he's just thinking of the past where sort of cases of underdetermination, empirical underdetermination, actually ultimately turned out to be cases of different on top people actually. So he's thinking about, the example, sort of Ptolemy versus Copernican universes or whatever equivalent, sort of Earth and geocentric and heliocentric cosmologies.
Lorentz and Einstein.
Yeah, and then eventually, I don't know about the point about that one was eventually observations. Once you could see sort of whatever the eclipses of Venus, right? You kind of knew what was going on the phases of Venus. Okay, then
so it was settled in favor of.
Yeah. So, I think I have what I would think was the answer to this question, but he wanted to know what your answer was to why the dualities aren't going to be like that, or why we shouldn't think that that's possible.
Oh, just because there's
better telescopes and find out how big the universe is.
Oh, they're sort of. There are exact scenarios, and the equivalences are for all possible observables. It was always the case that there could have been an observable that would distinguish some measurement you could make that would distinguish the Ptolemaic from the Copernican system. In this case, they're sort of entirely complete pictures, each side of the duality, each of the dual pair. There's the mathematical relationship, and there's the fact that it's like a complete set of observables. They're all identical. So I don't think it makes sense to say that you could ever settle one way or the other if they genuinely are exact dualities. I don't think it's coherent to say.
But let me press it a little bit on his behalf. Right, there's a slight equivocation on the word observable here, right? Because the results are for observable in the sense of, Hermitian operator in the quantum theory. And one might not think that corresponds to observable in the, pragmatic building apparatus to measure things sense. One might, in both directions, there may be Hermitian operators that are unobservable, and maybe there's observable things that go beyond the Hermitian operators.
Mm-hmm.
I don't know, maybe somehow the radius is directly observable?
The only way for that to be possible is if you're thinking something like T-duality accurately describes your world, and it's definitely a world of strings and these compact dimensions, and then you find that there are particles, and then the particles enable you to distinguish, right? You throw some particles in a world and you can very quickly say which one's which. It's only because you're dealing with restricting yourself to strings that you can't distinguish the differences in the different compact spaces, different compactified dimensions. So it would be some sort of external intervention where some new type of object served to distinguish what we thought was all the relevant structure, so they were equivalent with respect to all the then known relevant structure, and then some other piece of structure.
Yeah. I mean, that's what I think. I mean, you've read in my paper, right? I talk a lot about the Brandenburger and Vafer.
Yeah.
When you actually start to ask the question of how you would, I guess I'm talking to Josh as well, you know, how you'd start to operationalize actual measurements of the radius, you see you are brought exactly back to the quantum mechanical observables. And, I mean, that's their argument. Yeah. I think I even, well, it's obnoxious to plug your own papers, but you know, the other thing is somebody might think, well, maybe I can just directly sort of experience it. And I address that a little bit. But if you think your mind is a physical, you know, supervenes on a physical thing, that's not going to work either, because it's going to be described by the quantum observables as well.
Yeah, we need mind-body dualism. It's the only way.
Yeah, but then even then it's going to be weird. Even if your mind is sort of able to do something your body can't, but then there's not going to be any causal interaction between them, because that'll violate the quantum. I don't know. Whatever. There'll have to be mental interventions in the physical that aren't part of. Anyway. Okay.
But anyway, to answer that, so long as your duality is considered as a complete description and no external structure is introduced, then it's exact. And I do think it's incoherent to say that it could be settled.
Geneva.
I think we're out of time.
Oh, I guess we are actually. There's time for you guys to wrap up. Okay, Jake, did you want to have anything quick, or it is pretty much they're out of time now?
What do you think of the new hair, Chris?
I love it. You need to grow the beard, though.
I know. Pathetic.
Okay. All right. Well, cheerio, everybody. You can't see much. And thank you, Dean.